Across the western Pacific, few places experience the relentless forces of our restless planet with the same intensity as the Philippine archipelago. More than 7,000 islands rise from tropical seas that appear calm from above, yet the seafloor surrounding them tells a far more dramatic tale. Deep ocean trenches carve long scars through the Pacific basin. Massive slabs of Earth's crust move continuously, pressing, grinding, and diving beneath one another at speeds measured not in miles per hour or kilometers per hour, but in mere inches and centimeters each year. That motion may seem insignificant over the course of a single day, yet over decades and centuries it stores an extraordinary amount of energy. When that energy is finally released, entire regions can shake within seconds. That reality once again commanded attention during the early hours of the 5th of August, 2026, when a magnitude 6.3 earthquake struck approximately 20 miles or 32 kilometers southwest of Sarangani in the southern Philippines. According to the United States Geological Survey, the earthquake originated at a depth of approximately 6 miles or 10 kilometers, making it relatively shallow. Earthquakes occurring at such depths often produce stronger shaking near their epicenters than deeper events of similar magnitude, because seismic waves have less distance to travel before reaching the surface. Although earthquakes of this size are not unusual in the Philippines, every significant event immediately raises familiar concerns. Residents wonder whether stronger earthquakes may follow. Emergency officials begin checking for damage and casualties. Scientists rapidly analyze waveforms arriving from seismic stations around the world. Tsunami monitoring centers evaluate whether enough seafloor movement occurred to generate dangerous waves. Airlines, shipping companies, and local governments closely monitor official updates, while millions of people across the country ask the same pressing question. Why does the Philippines seem to experience powerful earthquakes so frequently? The answer is neither simple nor comforting. It lies within one of the most complicated tectonic environments found anywhere on Earth. Unlike regions influenced by only one major fault or a single plate boundary, the Philippines occupies an extraordinary geological crossroads where multiple tectonic plates interact simultaneously. Every movement along one boundary influences stress on another. Every earthquake becomes one small chapter in a much larger process that has shaped the islands for tens of millions of years and will continue long after modern civilization. By the 8th of August 2026, seismic records showed that the Philippine region had already experienced 13 strong earthquakes during the year. Each occurred under different geological circumstances. Some originated offshore near deep ocean trenches. Others struck along active faults cutting through populated islands. Several occurred at shallow depths, while others ruptured much deeper within descending slabs of oceanic crust. Although these earthquakes may appear connected simply because they occurred within the same country and within the same year, scientists emphasize that they are not necessarily part of one unfolding sequence. Instead, they reflect the remarkable complexity of an area where stress is constantly being redistributed through an intricate network of active faults and plate boundaries. Looking at a map of global earthquakes quickly reveals an unmistakable pattern. Rather than being scattered randomly across Earth's surface, earthquakes cluster into long belts that outline the edges of tectonic plates. One of the most active of these belts forms the famous Pacific Ring of Fire, a horseshoe-shaped zone stretching roughly 25,000 miles or 40,000 kilometers around the Pacific Ocean. It links New Zealand, Indonesia, the Philippines, Japan, Russia, Alaska, the western United States, Central America, and South America into one immense system where volcanic eruptions and earthquakes occur with remarkable frequency. The Philippines occupies one of the busiest intersections within this immense belt. From space, the archipelago resembles a chain of emerald islands scattered across brilliant blue water. Hidden beneath those waters are enormous geological structures that rarely appear in tourist photographs but dominate the region's seismic behavior. Deep trenches extend for hundreds of miles or hundreds of kilometers, marking places where sections of oceanic crust descend into Earth's interior. Large faults slice across islands from north to south. Offshore basins continue opening, while neighboring regions undergo compression. Few places combine so many active tectonic processes within such a relatively compact area. Understanding why requires looking beyond the islands themselves. Earth's outer shell is not one continuous piece of solid rock. Instead, it consists of numerous rigid tectonic plates floating atop hotter, weaker material within the upper mantle. These plates move continuously, driven by convection currents, slab pull, ridge push, and other forces operating deep inside the planet. Their average movement is astonishingly slow, often only a few inches or several centimeters each year. Yet because entire continents ride upon them, even this slow motion generates immense forces over geological time. Imagine placing two enormous sheets of rough sandpaper against one another and attempting to slide them past each other. Friction prevents smooth movement. Pressure steadily increases until resistance finally gives way. The stored energy is released almost instantaneously. Earthquakes occur through much the same principle. For years, decades, or even centuries, rocks surrounding a fault deform slightly while remaining locked together. They bend much like a wooden ruler slowly flexed under pressure. Eventually, the accumulated stress exceeds the strength of the rocks. The fault ruptures. Stored elastic energy radiates outward as seismic waves traveling through Earth's crust. People standing many miles away may experience only gentle swaying. Those closer to the rupture may endure violent shaking, capable of damaging buildings, roads, bridges, ports, and other critical infrastructure. In the Philippines, this process repeats again and again because tectonic plates never stop moving. To the east lies the vast Philippine Sea Plate. Farther east beyond that stretches the Pacific Plate, one of Earth's largest tectonic plates. To the west lies the Sunda Plate, often considered part of the larger Eurasian tectonic system. Between these major plates sits the Philippine Mobile Belt, a remarkably complex region composed of numerous crustal blocks squeezed from multiple directions simultaneously. Rather than functioning as one simple plate boundary, the archipelago behaves like an elaborate mechanical puzzle. Forces arriving from the east differ from those arriving from the west. Compression dominates in one location while sideways motion becomes more important elsewhere. Some sections sink, others rise. Mountains continue growing even as neighboring basins slowly deepen. One of the defining geological features east of the islands is the Philippine Trench. Extending for roughly 800 miles, or about 1,300 kilometers, this enormous trench marks a subduction zone where oceanic crust descends into Earth's mantle. Southward, it merges into other trench systems that continue influencing seismic activity around Mindanao. Another equally significant structure lies west of the archipelago. The Manila Trench stretches offshore along western Luzon, where another slab of oceanic crust also sinks into Earth's interior. Farther south, additional trench systems continue this pattern through the Sulu and Cotabato regions. These opposing subduction zones make the Philippines unusual compared with many other countries. Japan certainly experiences intense earthquakes, yet its tectonic setting differs. Chile experiences some of the largest earthquakes ever recorded, but most occur along one dominant subduction boundary. California's famous San Andreas Fault primarily accommodates sideways motion between two plates rather than opposing subduction systems. The Philippines experiences all of these processes in varying combinations. That complexity explains why earthquakes can originate from many different sources. One earthquake may occur as one tectonic plate dives beneath another. Another may rupture a large strike slip fault slicing directly across inhabited islands. Still another may occur deep within a descending slab hundreds of miles beneath the surface. Each follows different physical processes while contributing to the country's persistent seismic activity. The magnitude 6.3 Sarangani earthquake illustrates this complexity. Located offshore near southeastern Mindanao, the earthquake occurred close to one of the most tectonically active sections of the Philippine region. Here, multiple fault systems interact with nearby subduction zones, creating an environment where stress accumulates from several directions simultaneously. Scientists analyzing such earthquakes do far more than simply measure magnitude. Within minutes after rupture begins, seismic stations across the globe detect several distinct wave types traveling through Earth. Primary waves arrive first because they move fastest through solid rock. Secondary waves follow, traveling more slowly and unable to pass through liquids. Surface waves generally arrive later, but frequently produce the strongest shaking experienced by communities because they travel along Earth's exterior rather than deep within it. By carefully comparing arrival times at hundreds of monitoring stations, researchers calculate the earthquake's precise location, depth, and origin time with remarkable accuracy. Modern computing allows these calculations to be completed within minutes, providing emergency managers with essential information almost immediately. Magnitude itself represents only one part of the overall hazard. Depth often proves equally important. An earthquake measuring magnitude 6, occurring approximately 311 miles or 500 kilometers beneath Earth's surface, may be felt across enormous distances, yet produce relatively modest damage directly above its source. Conversely, a similar earthquake occurring only 6 miles or 10 kilometers deep can generate significantly stronger shaking across nearby communities. That is why the reported depth of the Sarangani earthquake immediately attracted attention among seismologists. Shallow earthquakes concentrate much of their energy close to the surface. Local geology then determines whether shaking becomes amplified or diminished. Soft sediments filling river valleys, reclaimed coastal land, and thick layers of unconsolidated soil can behave very differently from solid bedrock. In some locations, seismic waves become trapped and amplified, increasing shaking far beyond what nearby bedrock experiences. This phenomenon has repeatedly appeared during destructive earthquakes around the world. Entire neighborhoods built upon soft sediments sometimes sustain substantially greater damage than communities situated only a few miles or several kilometers away on more stable geological foundations. The Philippines contains many rapidly growing cities constructed across coastal plains, river deltas, reclaimed land, and volcanic deposits. Each possesses its own geological characteristics, influencing local earthquake behavior. Consequently, identical earthquake magnitudes do not always produce identical outcomes. Modern seismic hazard maps therefore incorporate much more than earthquake history alone. They include fault locations, trench systems, soil properties, crustal structure, expected ground acceleration, and thousands of geological observations collected over many decades. Engineers use these data when designing buildings intended to withstand future earthquakes. Yet despite increasingly sophisticated technology, one reality remains unchanged. Scientists can identify where earthquakes are most likely to occur over long periods. They understand why tectonic plates continue moving. They can estimate the likelihood of future ruptures along many faults. They can model tsunami generation and calculate expected ground shaking with impressive precision. They still cannot determine the exact day, hour, or minute when the next major earthquake will strike. That scientific limitation often frustrates the public, but it reflects the extraordinary complexity of Earth's crust. Every active fault contains countless irregularities. Rock strength varies from one location to another. Fluids circulate through fractures. Previous earthquakes redistribute stress in ways that remain difficult to measure directly. Tiny differences invisible, even to modern instruments, may influence precisely when a fault finally gives way. For the Philippines, where multiple tectonic systems operate simultaneously, that challenge becomes even greater. Every significant earthquake adds another piece to an immense geological puzzle that scientists continue assembling one event at a time. The magnitude 6.3 Sarangani earthquake is not an isolated anomaly, but another reminder that the archipelago occupies one of the most dynamic and closely watched seismic regions on the planet, where Earth's slow but relentless tectonic engine continues shaping the islands with every passing year. Even more remarkable is the fact that the Philippines does not rely solely on offshore subduction zones to generate destructive earthquakes. Running directly through the heart of the archipelago is another immense source of seismic danger known as the Philippine Fault System. Stretching for approximately 900 miles or more than 1,500 kilometers, this active strike-slip fault cuts across Luzon, Masbate, Leyte, and Mindanao. Unlike subduction earthquakes, which occur as one tectonic plate sinks beneath another, movement along this fault is primarily horizontal. Massive blocks of crust slide past each other, but friction prevents that motion from occurring smoothly. Instead, stress accumulates year after year until the rocks can no longer withstand the strain. When the fault finally ruptures, the release of energy can produce violent shaking across wide areas. Scientists often compare active faults to tightly compressed springs. Every year, the surrounding tectonic plates continue moving only a few inches or several centimeters, yet portions of the fault remain locked. The rocks bend almost imperceptibly while storing tremendous elastic energy. Residents living nearby notice nothing unusual. Roads remain intact, buildings stand undisturbed, and daily life continues without interruption. The process is almost completely silent. Then, within only a matter of seconds, decades or even centuries of accumulated motion are released all at once. Land on opposite sides of the fault may shift several feet or more than 1 meter during a single earthquake. Evidence of this relentless tectonic motion is visible across many parts of the Philippines. River channels become offset, mountain ranges continue to rise, valleys slowly change shape over thousands of years. Modern satellite positioning systems capable of measuring movement with astonishing precision confirm that different parts of the country are constantly moving relative to one another. Although these changes are far too small for people to notice from day to day, they reveal that stress is continuously building throughout the region. The recent magnitude 6.3 earthquake southwest of Sarangani occurred within a part of Mindanao where several active tectonic structures interact. Offshore trenches, regional faults, and the broader Philippine mobile belt all contribute to an environment where earthquakes are expected to occur. While it is natural for people to wonder whether one significant earthquake signals that another is imminent, seismologists urge caution when interpreting individual events. One earthquake can redistribute stress onto nearby faults, sometimes increasing stress in certain areas while reducing it elsewhere. The outcome depends on the geometry of the faults, the direction of movement, the amount of slip, and the characteristics of the surrounding rocks. Each event, therefore, becomes part of a much larger process that continues over decades rather than days. Historical records demonstrate that the Philippine archipelago has repeatedly experienced powerful earthquakes long before modern seismic instruments existed. Written accounts from earlier centuries describe churches collapsing, stone buildings cracking apart, landslides racing down steep mountainsides, and coastal communities enduring severe shaking. These historical observations, combined with geological evidence preserved within sediments and fault scarps, allow researchers to reconstruct centuries of seismic activity. The result is unmistakable. Large earthquakes are not rare exceptions within the Philippines. They are recurring features of the country's geological history. Some of the strongest earthquakes have originated offshore along major subduction zones, where enormous sections of oceanic crust rupture over distances measuring hundreds of miles or hundreds of kilometers. Others have occurred directly beneath populated islands as active faults suddenly slipped. Both types are capable of producing destructive consequences, although each behaves differently. Subduction earthquakes can sometimes generate tsunamis if significant portions of the seafloor move vertically. Strike-slip earthquakes, on the other hand, usually produce stronger localized ground deformation along the fault itself, although under certain circumstances, they may also contribute to tsunami generation if underwater landslides or complex fault movements occur. The 13 strong earthquakes recorded in the Philippine region by the 8th of August 2026 illustrate this diversity. Their magnitudes, depths, and locations vary considerably. Some occurred near eastern subduction zones facing the Philippine Sea. Others were associated with southern tectonic systems near Mindanao. Rather than pointing toward a single unfolding sequence, the collection reflects the reality of a nation surrounded by multiple active plate boundaries operating at the same time. For scientists, every one of these earthquakes contributes valuable information about the evolving distribution of stress across one of the world's most complex tectonic environments.